We're going to continue looking at 9.1, and we're going to look at how to convert from polar to rectangular, or maybe from rectangular coordinates back to the polar coordinates. And then we're also going to look at some graphs that you'll have to look at in 9.2. We won't be doing any graphing by hand. I'll show you how to use your calculator to generate those pictures. Conversion is actually a pretty important idea, especially if your next stop is calculus. Things are much easier to work with in polar, so very often you're given things in rectangular because that's what we're used to, and so that is kind of the easiest for us to visualize, but it's actually much easier to work it with our theta than it is with our xy. And all we need to do is use our basic trig functions, our sine and our cosine, and rewrite some of those rules that we had from SOHCAHTOA, from our right triangle trig. And so if I were to divide the r off on both sides, you'll see that you'll have x over r is equal to cosine, which we used to just call opposite adjacent over the hypotenuse. But when we were talking about our circle, that's a pretty poorly drawn circle, it was how far we are along the x-axis over our r for our radius instead of adjacent and opposite and hypotenuse. And of course, we would get the same thing for sine, where it's y over r is equal to sine theta. Now, on the unit circle, we just kind of said x is cos and y is sine, but that's because r was a 1. So we really didn't have to worry about it, but we'll need to remember that not everything is on a unit circle with a radius of 1. So the relationship between the sides will stay the same, but the radius will vary, and make a little bit more sense in a second. So if I have something that is in polar, and I tell you it's 2 pi over 4, and I want to convert that back over to rectangular so that it's maybe a little bit easier for me to figure out exactly where I need to go. I want to use x is equal to r cos and y is equal to r sine to kind of help me out. But I'm also going to want to think about where am I anchored, because that's going to help me work backwards sometimes as well. So this is in the first quadrant since it's a pi over 4. That makes life a little bit easier since everybody will be positive. I have my r and I have my theta, so all I need to do is use my conversion formulas. X is equal to r cos and y is equal to r sine, to go ahead and just crunch some numbers, and I can actually put all of that in my calculator. Or if it's on the unit circle, like pi over 4, I can just take out my unit circle and look at my values. R is a 2. The cos of pi over 4 is a radical 2 over 2. And because we're in the first quadrant and it's one of those 45-degree angles, it's the same, another positive radical 2 over 2. So you can give directions to that point by saying, hey, go open up to a degree of 45 and then head out 2 units. Or you can say, go over radical 2 to the right and up radical 2. So one kind of uses left rights and one kind of uses turns and lengths, if you will. And we'll talk a little bit more about that in class. If I'm given a rectangular coordinate, I'm in the Cartesian plane, and I want to go back to polar, I'm going to do the same thing, but I'm going to have to solve. So it's going to be a little bit more important for me to realize where I am. 2, negative 2 is down in the fourth quadrant. And that's going to be important because I'm looking for theta, and I'm dealing with sine and cosines. And so I'm going to have to use an inverse cos or an inverse sine. And if you're down in the fourth quadrant, you're going to want to solve using the inverse sine as opposed to using the cos. So remember, inverse cos goes from 0 to pi. Inverse sine goes from negative pi over 2 to positive pi over 2. So if you use the quote unquote wrong one, what you'll get is the reference angle. You may not get it in the right quadrant. And so if you're in the first quadrant, you can use either one. If you're in the second, you're going to want to use cosine. If you're in the fourth, you're going to want to use sine. If you're in the third, where neither one of them really quite work, I usually use both and kind of work backwards from there, but you could also use tangent. Now, the textbook and MyLabs Plus tends to like to use tangent. I don't like to use tangent. So the first thing I would do is find out what my R is. So I know I'm standing at the pole and I'm lassoing out to 2, negative 2. How long's the rope that I need if I'm going to stand at the pole and lasso out to that point? easy enough to find. 2 squared and negative 2 squared. I got an r of a 2 radical 2. And so I am down here at 2, negative 2, and now I know my r is, I'm going to write radical 8 just to keep it a little bit smaller. What I want to find out is this. So I'm going to write both of them. I know that x is equal to r cos theta, and y is equal to r sine theta. When you solve for these, it doesn't matter which one you use, and you can solve both, and you should land in the same spot, but it won't always look like you're in the same spot, but you'll wind up with the same reference angle as far as how far away am I from that x-axis. So x is a 2, r is a 2 radical 2. It's the theta that I'm looking for. Negative 2 for y, 2 radical 2 still for r, sine theta, and since I'm in the fourth quadrant, I'm going to use sine. Divide both sides by the 2 radical 2, and I'll get a negative 1 over radical 2, because those 2's will divide out. And if I rationalize that, I get a negative radical 2 over 2. I remember this one. I know this is on the unit circle, and it is the negative 45 degrees. But you can put in your calculator, which I will do right now. Maybe. There we go. I'll make sure it's on degrees. It's a little bit easier to see where you are in degrees, even though they often want the answer in radians. Make sure that looks pretty good, and I get a negative 45, and of course I know that has to be a negative pi over 4. I'll go back to this. Actually, before I go back to that, I'll show you what happens if you would have done that with cos. Actually, I will say second enter. Delete that. And say second cos. And you'll see you get the positive 45. So it looks like you're opening up a 45-degree angle. But I can't open up a positive 45 because that would put me up here, right? So you get the same picture, but it's upside down. It's facing the wrong direction. So I use a little bit of the algebra and a little bit of the unit circle and a little bit of the calculator to piece together where I am. So I know that if you were to say maybe like, not that you could take an absolute value of an angle, but the size of that angle and that negative gives it the direction the way down. Underneath my writing is they did the same thing as they just did it with tangent. I don't use tangent. And they wind up with the same thing. So you can say, hey, go over 2 to the right and down 2, or I can say open up a negative 45-degree angle and then lasso out a radius of a 2 radical 2. Either way, you'll land in the same spot. If you have an equation, what you're going to want to do is get your r's to look like either r squareds, or you're going to want to use them as a coefficient to in with the cosine. So if I want r equals 4 cos of theta, and I want to talk about this as a rectangular picture, so if I say graph y equals x plus 2, that's no problem for you. You know how to graph that. If I say graph r equals 4 cos theta, that's a little different. Let's look at what that graph would look like in our calculator. If you go to mode and go down to radian, make sure that guy's on radian, and then change this over to the third one, POL, that's pole. Now when you go to y equals, it's really r equals, so that's pretty cool. And when you hit 4 cos, and then you go to hit your variable button, the theta will pop up. And when you hit graph, here he comes. Now I would say the graphs are not always perfect. This is actually much more of a circle than like a little squished egg. Maybe we can try some zoom trig. Maybe that'll make it a little bit nicer. Oh, actually, that made it a lot nicer. So really it was just a circle that kind of got scooted over, right? Looks like it got scooted over maybe like 1 1/4. So how do you change that over to something that's a little bit easier to identify? You'll multiply through by the r, which may seem a little strange, but the idea is to square the r, but you can't just square r's. You can't just square the left side because then you would square the right side. So if I multiply both sides by r, I wind up with an r squared, which I know is x squared plus y squared from Pythagorean theorem. And I wind up with a very nice r cos theta over here, and I know that x is equal to r cos theta. So I can take the r squared out, put the x squared plus y squared in. I could take the r cos out, put the x in, and I know I'm dealing with a circle because both of these guys are squared, and I have an addition sign in the middle, and I'm not going to have any denominators when I clean this up. We'll talk more about conics and how to recognize what type of equation it is later on in the course in the next chapter. If I have 4xy equal to 9, and now I want to look at it in polar, we'll just do the exact opposite. If x is equal to r cos and y is equal to r sine, I'm going to take my x's and y's out, and I'm going to put my r's cos and r sine in. And so now I got 4r squared, because r times r, and then I got cos times the sine. And moving all of that stuff away from the r squared is not so bad. I can factor out the 2, and even come up with a 2 theta if you wanted to use some of those identity formulas. But you could divide both sides by 2 sine theta and take a square root if you wanted to, and now you have r and something that you could put in your calculator. We have some little rules of what the graphs will look like at the very end of the PowerPoint. I'm just going to show you a few of them. If I have r equaling a number, remember r squared is x squared plus y squared. So if you square both of these, if you kind of square both sides, you'll get an r squared is equal to a 9. Well, r squared is x squared plus y squared, and that's a circle. Remember, you're talking about a radius. And so if you're going to swing something around, you're going to wind up with something that looks like a circle, and we'll have a couple little divots here and there, and that kind of depends on the other terms that are in there. But anytime r is just equal to a number, think of it as I want a locus of points from a center where I am r units away. So I'm looking for everything that is 3 miles away from this particular center. A line will be just the theta. So if I have theta equaling just a number, an angle measurement, it's going to look very much like the line on the unit circle that matches that with both levers pulled for your radius. The other way that's pretty easy to swap this guy over so that you know you're looking at a line is to take the tangent of both sides, because tangent is sine over cosine, which in our Cartesian plane for our unit circle is y over x. And you're going to be able to look up what the tangent of any angle is, and then you would just multiply both sides. And so you're always going to wind up, if you have a theta equaling a angle measurement, with a line that's a direct variation going through the center. Not terribly exciting, I know, and I skipped a couple of slides where you could move that circle around, like we saw that one that went a little bit to the right or up or down. Those are all graphs that you can generate pretty easily in your calculator. So the more interesting stuff comes in when you have like binomials, or you have stuff that you're adding or subtracting onto the side. Now, of course, you can graph these in your calculator as well, but again, you always want to have a little bit of backstory so that you know what to expect when you put it in the calculator, so you know if you hit a wrong button or if you have to change a window, you know what kind of window you're looking for. So if I have 1 minus sine of theta, notice that my number here and my coefficient of my sine are the same. That's going to make a little difference. What happens in our graphs later on, I'll have a cardioid if I have 1 minus the sine. Now, they're going to walk you through in the textbook and maybe in the homework of how to sketch these things by hand, and it's going to feel a little bit like you're back in pre-calc algebra where you're picking thetas, plugging them in, and seeing what kind of points that you get out. But we can go ahead and put this in our calculator, and you see you got a cardioid. It looks like an apple to me, right? So it has a little dimple that it kind of gets pushed in. Sine, remember, kind of goes with our y. So when stuff is written in terms of sine, you're looking at things kind of going up and down, and cos being our left and our right. Negative would be our down. Positive would be up. So that would be my R1 is equal to a 1 plus sine. 1 minus cos would drag that guy, swing him to the left. 1 plus would swing him to the right. And you see how we're swinging around the pole in here. And there are our rules. If you have ones that the coefficient and the constant are not the same, who's bigger will make a difference. So Lemasson, I believe I'm pronouncing it correct, without an inner loop has my A value that is going to be bigger than my coefficient over there. And so it won't have an inner loop. It's going to look like a kind of like it got scooped out, right, a little bit. So it's kind of just got poked a little bit. That's 2 plus, so a minus 2 would be the other side. Sine would be up, positive 2 sine up, negative 2 sine down. And there are those rules. If you want an inner loop, notice now that the coefficient in front of the trig function has a higher absolute value than the constant, and that's going to create a pretty cool looking loop in there. And the calculator will graph the loop, so it's pretty cool. More examples of those. The rose petals. So this is a little bit like what we saw on that GIF that I have posted in Moodle. So I got 2 cos 2 theta. Remember, cosines are even functions, and we're talking about left and right normally with those. Calculator will graph these, so that's a wonderful thing. And it's a little hard to see what happens, but it will start at the origin, and it kind of starts to circle through. And so it will kind of go through like this and make the petals this way. Not the way that you might think, like if you remember making flowers in kindergarten, you did like this. Not like that. It's doing loops where it's swinging around like this. I've kind of missed my mark there. That's a little bit better. It will have, for cosines, it's going to have double the petals of what's on your inside there. So 2 cos 6 will have the oh no, 2 cos 4 is our first one, right? Because I got 8 petals. 6 theta, 12. Now, but the 3 and the 5s, when they're odd, they're actually just the number that they have. Sine is not a rose petal. It's more like a stacked infinity symbols, I guess, for a better description. See how it kind of goes further out like that? And then there's the spiral. And so I have E theta over 5. And that will just loop around forever and forever. And if we had time to talk about compound interest, we could use a logarithmic style. You do not need to memorize these kinds of things. There's a lot at the end. You got a couple of slides that tell you what the type of equation they'll be, what they look like, what their symmetry is, and you can print those out. This is not something that you need to commit to memory. I doubt there's anybody in the office somewhere graphing roses with 3 petals on a calculator. So when you're going through 9.2, you just want to be able to start to recognize the graphs and some of their properties, not be able to memorize them.